All right, let's say one more thing about Jordan Holder series before moving on to a slightly different topic, which we will soon after tie back to this. Anyways, if G has a Jordan Holder series, then any strictly decreasing saying composition series can be refined to a Jordan Holder series. And to see this, okay, so let's say we have sigma 1 here, we have sigma 2. Sigma 1 is going to be Jordan Holder. Sigma 2 is going to be strictly decreasing. I'll just write SD. Then we've got sigma 1 prime, sigma 2 prime, and these two are equivalent. So how does this proof go? So when I say a corollary, this is a corollary of the result from the previous video. So of course it's a little unfortunate to break it up between two videos, but it's not a corollary in the strict sense. You're not applying the last result. It turns out that the proof is very similar. Because what you do, here, let's draw a line between these to show that this is just a diagram. So I'm not actually going to write this proof out, I'm just going to discuss it. Because it's similar to the previous one, which, of course, for that I didn't write out a bunch of things. But whatever. So, equivalent refinements. We know that the graded pieces of these two are the same. So, let's see here. So, what do the graded pieces of sigma 1 prime look like? Well, sigma 1 is a Jordan Holder series, so all of its graded pieces are simple. So, the graded pieces of sigma 1 prime is you've got a whole bunch of trivial ones and you've got a whole bunch of simple ones. So similarly, if you look at the graded pieces for sigma 2 prime, a bunch of them are simple and a bunch of them are trivial. Now we know that sigma 2 is strictly decreasing, so none of the trivial ones here were there to begin with. And so let's choose another. Let's make another composition series out of sigma 2 prime, where we go through and every time we see a trivial graded piece, we throw out one of the subgroups that made up that graded piece, but we don't throw out anything that came from sigma 2. We only throw out things that we added in there to obtain this refinement, sigma 1 prime or sigma 2 prime. So can we guarantee that if you do this process, you'll never be forced to throw out an element of sigma 2? Well, yes, because if it were the case that you were forced to throw out some element of sigma 2, that means that you have two subsequent subgroups in sigma 2 prime where the quotient is trivial, and both of these, both the subgroup and the one that you're quotienting by, came from sigma 2. That's the only scenario where you're forced to throw one of these out, some element of sigma 2 out. But this scenario can never happen because we assume that sigma 2 is strictly decreasing. And so you can do this process. You can take sigma 1 prime and you can throw out, every time you have a trivial quotient, you can throw out one of the subgroups without throwing out anything that came from sigma 2. So when you do this, what you're going to end up with is you're going to end up with another, let's say, sigma 2 double prime. So I put this line this way because sigma 2 prime is a refinement of sigma 2 double prime. And when I say refinement, that should sort of hint at, it turns out sigma 2 double prime is in fact a composition series. You don't know that to begin with, but the fact that you're throwing out elements of trivial graded pieces, we did an argument like this previously where we had to throw out things and prove that we still had a composition series, and that's because if you're throwing out something that was in a trivial that's part of a trivial quotient, then when you look at everything else, you'll still have normal inclusions because you had a normal inclusion from the thing that was, because the quotient was trivial, these two subgroups were the same, and you had normality in both directions, and so if you throw out one of them, you still get normality. And so you have sigma 2 double prime, it's a composition series, and and sigma 1 prime is a filtration of it. But you also know that that you didn't throw out anything that came from sigma 2. So in fact, this is a refinement. So sigma 2 double prime is a refinement of sigma 2. Sigma 1 prime is a refinement of sigma double prime. And let's see here. So we took sigma 2 double prime, and the way we got it was we took it has all the same graded pieces as sigma 2 prime, but we threw out all of the trivial graded pieces. But then we know that sigma 2 prime, all of its graded pieces are either trivial or simple. And so for sigma 2 double prime, if we threw out all the trivial ones, then the only graded pieces remaining are simple. And so sigma 2 double prime is a composition series that is a refinement of sigma 2, and because all of its graded pieces are simple, we know that it's a Jordan-Holder series. And that does it. That proves that we can take any, if we have a Jordan-Holder series and we have a composition series here, then we can refine it to a Jordan-Holder series. And so there you go. And certainly you need this Jordan-Holder series here to exist. In the proof we need it because that's how we got that these graded pieces were simple. We got them from sigma 2 prime, which we got from sigma 1 prime. And furthermore, you know that this is necessary because you know that every group has a composition series, but not every group has a Jordan-Holder series. Okay, so that takes care of that, and now let's switch gears. Let's talk about the commutator subgroup. So, if G is a group, the commutator subgroup is, let's see here, we can write it as D of G, and this notation comes from the fact that this used to be called, apparently these used to be called derived groups, but I think that the word derived just gets thrown around all the time in mathematics, so I think people have moved away from that. But anyways, it's a subgroup generated by elements of the form A, B, A inverse, B inverse, where A and B are both elements of G. And certainly it's a subgroup because, it's a subgroup generated by it's a group generated by a subset of G. Okay, so claim, see here. So if we have two normal subgroups A and B of G, and we define A comma B, and this we'll actually use a lot in the future. So it's good that we're defining this now. A, B, A inverse, B inverse, where A is in A and B is in B. It's not a subgroup, it's an element. Then this is normal in G. Okay, and so in particular, what does this tell us? In particular, this tells us that the commutator subgroup is normal in G because you just let A equal B equal G, and certainly G is normal in itself, and so then this is just the commutator subgroup. Okay, and how do we prove this? We prove this using a previous homework exercise. And I'll probably put a video of this up at some point, but I'm just going to reprove it now. So let's see here. So let X be the collection of things of the form A, B, A inverse, B inverse. A is in A, and B is in B. Okay, so let G be in G and A, B, A inverse, B inverse be in X. Then we take G, A, B, A inverse, B inverse, G inverse. What we're trying to prove is that X is closed under conjugation. Probably should have mentioned that, but I didn't. Oh well. So what we do is this is just GA G inverse, GB G inverse, GA G inverse, inverse, GB G inverse, inverse. And why is that? That's because what have we done here? We've taken, we have this GA, this is fine. Between A and B, we inserted G inverse G, which is fine because that's 1. Between B and A, we inserted G inverse G. Between A inverse and B inverse, we inserted G inverse G. And then we just ended up with B inverse G. And then if you do that, then like you can see that here, this is GA, A inverse G, B, G inverse GA, then, oh, well, wait a minute. Right, because when you take this inverse, here this becomes G, A inverse, G inverse. So G, B, G inverse, G, A inverse, G inverse, and then again, taking the inverse of this, you get G, B inverse, G inverse. And so that's why these two things are equal. And obviously, GA G inverse is in A since it's normal. And GB G inverse is in B because B is normal. So then this is in AB A inverse. This is an element of the form AB A inverse B inverse. And so this is an X. So X is closed under conjugation. Okay. E is in A intersect B because A and B are normal subgroups, so they contain the identity. So E is, watch this, E is E inverse, and that's contained in X. Okay, so the identity is in X. All right. Now so what are we trying to prove? So let X be in subgroup generated by X. Well, we want to prove, oh, that's bad because, well, whatever. Okay, so I'm going to try to differentiate between my lowercase x's and my uppercase x's as best as I can, but it's not going to be perfect. So what we want to prove, let's see here, A comma B is the subgroup generated by AB A inverse B inverse, where this thing. So A comma B is precisely the subgroup generated by X. So we want to prove that this is normal in G. So let X be in this subgroup. Then we can write X as a product from I equals 1 to n of xi for some x1 through xn in X. And the way we can do this is because this is the subgroup generated by X, so it contains all finite products of things in the set X as well as the identity. But since the identity element is in there, we can just write it like this. And the reason I went through all the trouble to point that out is because that makes things a little easier. Okay, so we have this. Then for all G in G, we have, let's conjugate by G, let's conjugate X by G and see what we get. This is G times the product from I equals 1 to N, Xi, G inverse. But let's see here. Between every single one of these, you can just insert a G inverse G. So you could get, like, instead of taking the product of x1 through xn, you could take x1 G inverse G, x2 G inverse G, x3 G inverse G, and G, and then so on. So then what you'd end up with is you'd have G x1 G inverse G x2 G inverse G x3 G inverse all the way up through G xn G inverse. And if you combine that into one product, you have the product from I equals 1 to N of G xi G inverse. But this is just a product of elements in, let's see here. We know that X is closed under conjugation, and so this is a product of elements in X. But that's precisely what this is. So then this is in the subgroup generated by X. Hence, we have that this subgroup A comma B is equal to the subgroup generated by X is normal in G. And that's exactly what we wanted to prove. All right, and let's see here. We did not get as far as I was expecting, but we have this result. And now we'll go forward from here and see what we can do with commutator subgroups and with this thing here.